this video, I will solve common problems 41, 48, 59. 41 is this integral you see here, and this should remind you something of the type you have u prime over u, because the derivative of 7 to the 2x is not exactly 7 to the 2x, but it's quite similar. This is derivative of the exponential, it's the exponential, times the log of the base, times the derivative of 2x, which is 2. So if we make u equals to the denominator, 5 plus 7 to the 2x, we have the u prime is, let's rewrite this in a different way, 2 times ln 7, 7 to the 2x, which is almost the numerator. So to do the integral, we just copy here 7 to the 2x over 5 plus 7 to the 2x dx. And what are we missing? We're missing this part here. So changing color to red, we put whatever I'm missing, 2 times ln 7 in the numerator and 1 over 2 times ln 7 outside to cancel it out. So now we have is 1 over 2 times ln 7 integral u prime over u, and this is the log. So this is 1 over 2 times ln 7 ln absolute value of u, which is 1 over 2 ln 7 log of 5 plus 7 to the 2x plus c. This is u, but u is always a positive number, so the absolute value of u is equal to u in this case only. This is an easy application of the fundamental theorem of calculus. Remember, we have seen shortly in class that the fundamental theorem of calculus says that if f prime is equals to f, then the integral between a and b of small f is f of b minus f of a. As notation, we write this as fx between a and b. So in our case, we have 0 to 3 e to the x dx. Now the integral of e to the x is precisely e to the x because the derivative of e to the x is also e to the x. Let's separate this. So this will be, this is a small f and this is capital F in this case. In this case, a small f is equals to capital F. Okay, so this is e to the x between 0 and 3, which is e cubed minus e to the 0. This is 1, so that will be e cubed minus 1. Problem is an application of the fundamental theorem of calculus to compute areas. So what you have to do is find the points of intersection between these curves. This is a parabola, this is a vertical line, and this is a hyperbola. Okay, this parabola is something like this. This vertical line and the hyperbola is this one here. So the intersection will take first on this first quadrant, and we first try to find what are the common points of the parabola and the hyperbola. Rewrite this as y equals x squared and y 1 over x. So we have x squared equals 1 over x, x to the 3 moving this x up, x to the 3 equals to 1, x equals to 1. So here we have the graph of this thing, which is the parabola. The right hand side is the one that matters for us. Then we have the hyperbola. This point is 1, and so is this one. And then here, the line x equals to 2. So this area we have to compute, we'll divide it in two parts. This one here, and this one up to here. So we'll compute this A1, and then compute A2, and our area is simply the addition of A1 and A2. So how do we compute A1? A1 is the integral between this point 0 to this point 1 of the parabola. That's what it is. So x squared dx, so that's x to the 3 over 3 between 0 and 1, 1/3 minus 0/3 equals to 1/3. For A2, we have the integral from 1 to 2 of this curve here, which is the hyperbola, 1 over x dx. So that's the log of absolute value of x between 1 and 2. So the log of 2 minus the log of 1, which is 0 log of 2. And what area we're looking for will be a1 plus a2, which is simply 1/3 plus the log of 2.